Welcome back to the Deep Dive, where we take complex systems, grab the best available sources, and, well, we really distill the knowledge until you feel truly informed.
And today, we are really diving deep, aren't we? We're tackling the body's ultimate logistics and infrastructure project, the cardiovascular system.
Exactly. If you really want to understand how life is sustained, this is the foundational network.
It truly is.
Let's try and unpack this with an analogy.
Right.
It helps, I think. Imagine your body as this huge, complex, self-sustaining city.
Okay.
The skeleton is the architecture, the buildings, the brain, that's the control center, City Hall maybe, and the cardiovascular system.
That's everything else vital.
Pretty much. It's the entire critical infrastructure, the transportation network, the power lines for energy delivery, and the waste management system, all rolled into one incredibly efficient package.
That's a great way to put it. If the transport shuts down.
Exactly. The city starves or it drowns in its own waste. It's that fundamental.
So our mission today is to explore that powerful pump, the heart, and the huge network of vessels, the roads that keep everything going.
And crucially, how they regulate themselves. We want to move beyond just definitions, right?
Right. We want to give you the fundamental insights into its complex, its autonomous operation, how it all works together without you even thinking about it.
And the scale we're talking about here is it's genuinely mind-boggling. We're looking at a pump roughly the size of your closed fist.
Tiny, really.
Yeah. But it generates enough pressure to push blood through something like 100,000 kilometers of vessels.
It's almost unbelievable. That's enough roadway to circle the Earth, 2.5 times?
Incredible. And it just keeps going.
Oh, absolutely. That pump is tireless. It'll contract and relax roughly 2.5 billion times in an average lifespan. Billion.
Without needing a service contract.
Exactly. And its core functions, the things we'll explore today, are actually quite simple on the surface. Pumping the blood.
Okay, function one.
Transporting it through all those vessels. Exchanging nutrients and wastes way down at the microscopic level in the capillaries.
Yeah.
And number 4, constantly generating and monitoring the pressure and the rhythm needed to keep that flow going.
Pumping, transporting, exchanging, generating pressure. Got it. That's our roadmap. Okay, so let's start right there in the engine room, the heart itself. Now, you might think it sits, smack dab in the middle of your chest.
What people do, yeah.
But it actually lives in a very specific spot, slightly offset in the chest cavity. So where exactly is this incredibly hardworking organ located?
Right. It's housed within a space called the inferior mediastinum.
Mediastinum.
Yeah, the mediastinum literally means middle partition. Think of it as the central service corridor running right down the midline of your chest.
Like a utility shaft in a building.
Exactly like that. It contains the heart, obviously, but also the major great vessels, the aorta, the vena cava, and other key passageways like your windpipe, the trachea, and your food pipe, the esophagus. It's a busy neighborhood.
So we can picture the boundaries pretty easily then. Your breastbone. The sternum, that's the front wall.
Correct.
Your spine, the thoracic vertebrae, forms the back wall. And the 2 lungs, kind of nestled in their own cavities, flank it on the sides.
Precisely. It's really well protected in that central spot, and it rests directly on the diaphragm, that big muscle that forms the floor of your chest cavity.
Okay.
Now, here's the interesting detail about its position. Even though it's small, only about 250 to 300 grams, like a large apple or your fist. 2/3 of its mass actually tilts distinctly over to the left side of your body's midline.
So it's not perfectly centered. That explains why you usually feel your heartbeat strongest on the left side, doesn't it?
That's exactly why. That leftward tilt is key.
Okay, that slight tilt makes a lot of sense, especially when we think about what the left side has to do later. So moving from where it is to what it is. The heart is this highly specialized piece of muscular architecture. How is the wall itself built to handle that constant, forceful squeezing?
It's built in layers, like a reinforced wall. There are 3 main layers.
3 layers, okay.
The outermost layer is called the epicardium. Epi means upon or outer. Interestingly, this is actually the inner layer, the visceral layer of the protective sac that surrounds the heart.
Okay, so the outer layer of the heart wall is the inner layer of its covering. A bit confusing.
It can be at first, yeah. Just think of it as the layer touching the heart muscle itself on the outside. Then inside that, you have the real powerhouse, the middle layer, the myocardium. Myo means muscle.
Ah, so that's the muscle bit.
That's the muscle bit. It's thick, strong, and it's the tissue responsible for the actual contraction. It makes up most of the heart's bulk. It's the workhorse.
The workhorse, I like that. And the innermost layer.
That's the endocardium. Endo means within. It's a thin, very smooth layer that lines all the chambers and covers the valves.
And that smoothness is important, right?
Right.
To prevent clots and reduce friction as blood flows through.
Absolutely crucial. You want smooth flow. Now, surrounding all of those layers, you have the protective casing I mentioned, the pericardium. Peri means around.
The sac itself.
The sac itself. It actually has two main parts. There's an outer, tough, fibrous layer, the fibrous pericardium, which anchors the heart and prevents it from overfilling.
Okay, like a tough outer shell.
And then deeper inside that is the serous pericardium. This is the part that's actually double layered.
Double layered.
Yeah, it has an outer parietal layer that lines the fibrous sac and an inner visceral layer, which is the epicardium we already mentioned, remember?
Ah, right. The outer layer of the heart is the inner layer of the serous sac. Got it.
Exactly. And between those two serous layers, the parietal and the visceral, there's a tiny space filled with a thin film of pericardial fluid.
And that's the lubrication.
That's the critical lubrication. It allows the heart to beat constantly, 2.5 billion times, without rubbing and generating damaging friction against the surrounding tissues. It's like engine oil on an industrial scale. Hashtag tag 1.3, the 4 chambers and valves. Plumbing system.
Okay, lubricated and ready to pump. Let's get into the core plumbing now. The 4 chambers and the valves that control the traffic flow. How is this system set up?
It's actually quite elegant. You have 2 receiving chambers up top, called the atria, and 2 more powerful discharging chambers down below. The ventricles, think top floor for receiving, bottom floor for shipping out.
Atria receive, ventricles eject. Simple enough.
And the atria generally have thinner walls. They're more like collecting reservoirs.
Makes sense. They don't need to push hard.
Exactly. The right atrium on the right side collects all the deoxygenated blood that's coming back from the entire body. It arrives through 2 massive veins, the superior and inferior vena cava.
Superior from the upper body, inferior from the lower.
Correct. And crucially, the right atrium also receives the deoxygenated blood from the heart muscle itself via a vessel called the coronary sinus. We'll come back to that.
Okay, so all the used blood ends up in the right atrium. What about the left?
The left atrium is the receiving chamber for the freshly oxygenated blood coming back from the lungs. This arrives via 4 pulmonary veins.
4 veins bringing good stuff from the lungs. Got it.
Now, when we move down to the ventricles, the discharging chambers, the difference in their structure is really striking.
Yeah, go.
The right ventricle pumps that deoxygenated blood it received from the right atrium, but only to the nearby lungs. That's a relatively short trip, a low-pressure system. So its wall is muscular, but not excessively thick.
Okay, short commute, less muscle needed.
Right. But the left ventricle, well, that's a different beast altogether. It receives the oxygenated blood from the left atrium and has the monumental task of pumping it out to the entire rest of the body, head to toe, against much higher resistance.
So it needs to be way stronger.
Way stronger. Its wall is significantly thicker, much more muscular. It's built like a tank, really. This chamber forms the apex, the pointy bottom tip of the heart you often see in diagrams. It's the true power generator of the whole system.
And that thickness difference directly relates to blood pressure readings, doesn't it? That high systolic number comes from the left ventricle's massive push.
Absolutely. That 120 millimilli Hg systolic pressure, that's the peak force from the left ventricle. Now, with all this powerful pumping, you need precise traffic control. You can't have blood flowing backward.
Right. That would be inefficient or worse.
Exactly. And that's the job of the cardiac valves. Think of them as one-way doors or gates. They ensure blood moves forward through the chambers and out into the arteries and never back the way it came.
So how many valves are there and where are they?
There are 4 valves organized into 2 sets. First, you have the atrioventricular valves, or AV valves. These sit between the atria and the ventricles.
Okay, controlling flow from the receiving rooms to the pumping rooms.
Precisely. On the right side, between the right atrium and right ventricle, you have the tricuspid valve. It's called that because it has 3 flaps, or cusps.
Try for 3, makes sense.
On the left side, between the left atrium and left ventricle, you have the bicuspid valve because it has 2 flaps. This one is also very famously known as the mitral valve.
Mitral valve. Okay, I've heard that one. 2 flaps on the left, 3 on the right.
Correct. Now imagine the massive pressure when the ventricles contract. What stops these AV valves from just blowing upward back into the atria like saloon doors swinging the wrong way?
Good question. There must be something holding them.
There is. Attached to the edges of these valve flaps are tiny white fibrous cords called chordae tendineae. They look remarkably like parachute strings.
Parachute strings, okay.
And these strings are anchored down below to little bumps of muscle projecting from the inner walls of the ventricles. These muscular bumps are called the papillary muscles.
So the muscles pulling the strings which hold the valve flaps shut.
Exactly. When the ventricles contract, the papillary muscles also contract, tightening the chordae tendineae, which prevents the valve cusps from prolapsing or bulging back into the atria. It's a very clever tethering system ensuring one-way flow under high pressure.
Prevents backflow or regurgitation.
Got it.
That's the first set of valves. What's the second?
The second set guards the exits from the ventricles into the major arteries. These are called the semilunar valves.
Semilunar, half-moon shaped.
Precisely. They look like little crescent moons.
Oh.
The pulmonary semilunar valve sits at the exit of the right ventricle, leading into the pulmonary artery, which goes to the lungs.
Okay.
And the aortic semilunar valve guards the exit of the powerful left ventricle, leading into the main artery, the aorta.
And how do they work? No strings attached.
No strings here. Their shape is key. When the ventricles contract and eject blood, the pressure pushes these valves open flat against the artery walls. But as soon as the ventricles relax and the pressure inside them drops, the backflow of blood trying to leak back from the arteries fills up these little half-moon cusps and snaps them tightly shut. It's purely pressure operated. Hashtag 1.4 the foundation, fibrous skeleton.
Okay, chambers, valves, the whole plumbing setup seems clear. But you mentioned something earlier about insulation.
Ah, yes. Before we move on to the vessels, the roads, we absolutely have to talk about the heart's hidden backbone, the fibrous skeleton. It's often overlooked, but it's incredibly important.
Fibrous skeleton. Sounds structural. What is it made of?
It's essentially rings of dense connective tissue, like tough cartilage, that surround all four valves at the junction between the atria and the ventricles.
Okay, so it anchors the valves.
That's one crucial role, yes. It provides a strong structural foundation, keeping the valve openings from stretching or getting distorted under the constant pressure changes. It maintains the heart's shape around the valves.
That makes sense. Keeps the doors fitting properly in their frames.
Exactly. But its other role is arguably even more critical, especially for how the heart functions as a pump.
Which is?
It acts as an electrical insulator, a non-conductive barrier like rubber around a wire.
An electrical insulator. Between what?
Between the muscle tissue of the atria up top and the muscle tissue of the ventricles down below.
Wait, why is that so important? Why block the electrical signal? Wouldn't you want it to spread easily?
But think about the timing. If the electrical signal that tells the muscle to contract could just spread instantly from the atria straight down into the ventricles.
They'd contract at the same time.
Exactly. The atria and ventricles would squeeze simultaneously. Imagine trying to fill a water balloon while you're already squeezing it shut. It would be completely ineffective as a pump. You wouldn't get proper filling.
Right, you need the top chambers to finish filling the bottom ones before the bottom ones squeeze.
Precisely. The fibrous skeleton acts like an electrical firewall. It prevents the main wave of electrical activity from passing directly down. Instead, the signal is forced to go through one specific controlled gateway, a structure called the AV node, which we'll discuss in the electrical part.
And that forces a delay.
Yeah. It forces a crucial, tiny delay, just enough time for the atria to finish their contraction, topping off the ventricles, before the massive ventricular contraction begins. This insulation is the non-negotiable structural basis for the heart's coordinated sequential pumping action. It's all about timing.
Okay, wow. That fibrous skeleton is way more important than it sounds. So we have this perfectly timed, powerful engine. Now let's look at the vast infrastructure it serves, that incredible 100,000-kilometer road network. The blood vessels.
Right. The highways, roads, and tiny delivery alleys.
But hold on, before we hit the main roads, the engine itself needs fuel, right? How does the heart muscle get its own supply of oxygen and nutrients? Hashtag 2.1, the heart feeds itself. Coronary circulation.
That's a fantastic point, and it's one of the first things that surprises people. That thick heart muscle, the myocardium, it actually cannot get enough oxygen and nutrients just by diffusion from the blood flowing through its chamber.
Really? Even with all that blood rushing past?
The muscle wall is simply too thick. Diffusion wouldn't penetrate deeply or quickly enough. So the heart needs its own dedicated plumbing system. The coronary circulation. Corona means crown, as these vessels encircle the heart like a crown.
Ah, Okay, so where do these coronary arteries come from?
They branch off right at the very beginning of the main highway, leaving the heart the ascending aorta. Almost immediately after blood is ejected from the left ventricle, the first two side roads peel off. These are the left coronary artery and the right coronary artery.
Okay, a left and a right main supply line.
Exactly. The left coronary artery is particularly vital because it feeds the high-demand, high-pressure left side of the heart. It usually splits very quickly into two major branches.
Which are?
The first is the anterior interventricular artery. You often hear this called a LAD for left anterior descending.
The LAD. I've heard that sometimes called the widowmaker artery.
Sadly, yes. Because it supplies such a large portion of the powerful left ventricle, as well as parts of the right ventricle wall, a sudden blockage in the LAD can be catastrophic. It disrupts the main pump significantly.
Wow. Okay, so the LAD is a critical branch.
Right.
What's the other branch from the left coronary artery?
That's the circumflex branch, which curves around to supply the left atrium and the back of the left ventricle.
Got it. So the left coronary artery takes care of most of the left side. What about the right coronary artery?
The right coronary artery supplies the right atrium and most of the right ventricle. It also gives off key branches like the posterior interventricular artery, which often meets up with the LAD, and the marginal branch.
So these arteries deliver the oxygenated blood. How does the used blood get collected from the heart muscle?
Efficiently. Most of the deoxygenated blood carrying waste products from the heart muscle drains into several cardiac veins. These veins then converge into a large collecting vessel on the posterior side of the heart called the coronary sinus.
Coronary sinus, okay.
And this coronary sinus conveniently empties directly back into the right atrium, along with all the other deoxygenated blood returning from the body, so it rejoins the main circulation right away.
A neat little loop. Feed itself first, then collect the waste and put it back in the main return flow.
Precisely. And there's another clever feature built into this coronary road network, something called anastomosis.
Anastomosis, what's that?
It means the arteries connect and form networks or loops with each other. So different branches of the coronary arteries actually interconnect. This creates what we call collateral circulation.
Lateral, like backup roads.
Exactly like backup routes. If one small branch starts to get narrowed or blocked, say by a plaque buildup, these interconnections can sometimes provide an alternate pathway for blood to reach the heart muscle beyond the blockage.
So it's like having built-in detours or bypasses. That's a great safety feature.
It's a crucial safety feature. It doesn't always prevent damage, especially with sudden, large blockages, but it can certainly help minimize the extent of injury and buy valuable time. Hashtag 2.2 vessel microstructure, arteries, capillaries, veins.
Okay, the heart feeds itself. Now let's look at the main road network, the structure of the arteries, capillaries, and veins themselves. Do they all have the same basic construction?
They share a fundamental three-layer design, yes. These layers are called tunicas.
Tunicas, like coats.
Exactly. The innermost layer, lining the vessel, is the tunica intima. It's primarily a smooth layer of epithelial tissue called endothelium, which minimizes friction.
Smooth inside. Got it.
The middle layer is the tunica media. This is mostly smooth muscle and elastic fibers. This layer is usually the thickest and varies the most between vessel types.
Muscle and elastic.
Yeah.
Sounds important for controlling the vessel.
Very important. And the outermost layer is the tunica externa or adventitia. This is mainly connective tissue, collagen fibers that protect and anchor the vessel.
Intima media externa. Okay. Yeah. How do these layers differ in arteries versus veins?
Big differences related to their function. Arteries carry blood away from the heart, usually under high pressure, so their walls, especially the tunica media, are much thicker and stronger than veins.
Built to withstand pressure.
Right. The largest arteries, like the aorta, have a huge amount of elastic tissue in their tunica media. This allows them to stretch significantly when the ventricle ejects blood, absorbing that pressure surge, and then recoil elastically during diastole. This recoil helps maintain blood pressure and keeps the flow moving forward smoothly, even when the heart is relaxing. It evens out the pulses.
So the elasticity acts like a shock absorber and helps push blood along.
Perfectly put. Now, as arteries branch and get smaller, they become arterioles. These are like the smaller roads leading into neighborhoods. Their tunica media is less elastic, but very rich in smooth muscle.
Why more muscle there?
Because these arterioles are the primary control points for blood flow distribution and overall blood pressure.
Yeah.
By contracting or relaxing that smooth muscle, the body can dramatically change the diameter of the arterioles.
Making the road wider or narrower.
Exactly. Constricting the arterioles increases resistance to flow, which raises blood pressure system-wide. Dilating them decreases resistance and lowers pressure. This ability to change resistance is called peripheral resistance, and it's a key factor in blood pressure regulation. They are the main traffic controllers.
Okay, arteries handle pressure, arterioles control flow and resistance. What about the tiniest vessels?
The capillaries. These are the truly functional units of the whole system. This is where the real business happens, the exchange zone.
Where the deliveries are made and the trash is picked up.
Precisely. Capillaries are microscopic, barely wide enough for red blood cells to squeeze through in single file. And their walls are incredibly thin, just a single layer of endothelial cells, basically only the tunica intima.
Just the inner lining. Why so thin?
To allow for rapid diffusion, oxygen and nutrients need to pass easily out of the blood into the surrounding tissues, and carbon dioxide and waste products need to pass easily into the blood from the tissues. That thin wall minimizes the distance for exchange.
Makes perfect sense.
Yeah.
It's all about efficient transfer.
Right. And blood flow into these capillary networks, or beds, isn't constant. It's controlled by tiny rings of smooth muscle at the entrance to the bed called precapillary sphincters.
The gatekeepers.
Little gatekeepers or traffic lights. If the tissue needs oxygen and nutrients, say, a muscle during exercise, these sphincters relax, opening up the capillary bed, and blood rushes through perfusion.
Okay.
If the tissue is resting and doesn't need much flow, the sphincters contract, largely bypassing that capillary bed and diverting blood to areas where it's needed more. It's an incredibly efficient way to match blood supply to metabolic demand, moment by moment.
Wow. So the body is constantly rerouting traffic based on need.
Constantly. And not all capillaries are built the same either. They're specialized for their location. Most are continuous capillaries with tightly joined cells found in skin, muscles, lungs, and the central nervous system.
Okay, the standard model.
Then you have fenestrated capillaries. Fenestra means window. These have small pores or windows right through the endothelial cells, making them much leakier. You find these where rapid filtration or absorption is needed, like in the kidneys, the intestines, and endocrine glands that release hormones into the blood.
Pores for faster exchange. Makes sense for kidneys.
And finally, there are sinusoids. These are the leakiest of all. They are wide, winding capillaries with large gaps between the cells and an incomplete basement membrane. They allow even large molecules and blood cells to pass through their walls.
Where would you need something that leaky?
Places like the bone marrow, where new blood cells need to enter circulation, the liver, where blood needs to be processed, and the spleen, where old blood cells are removed.
Okay, different capillary types for different jobs. You mentioned the central nervous system has continuous capillaries. Is that related to the blood-brain barrier?
Absolutely. The blood-brain barrier is formed by those continuous capillaries in the brain, but with an extra feature. Their endothelial cells are joined by extremely tight junctions, and they're surrounded by processes from brain cells called astrocytes.
Making them extra selective.
Extremely selective. This barrier tightly regulates what substances can pass from the blood into the brain tissue, protecting the delicate neural environment from toxins, pathogens, and even fluctuations in blood chemistry.
A critical security checkpoint for the brain. But I guess it also makes it hard to get medications into the brain sometimes.
That's the downside, yes. It's a major challenge in treating brain diseases.
Okay, so that covers arteries, arterioles, and capillaries. What about the return trip? The veins?
Right, the veins collect blood from the capillaries and venules, the smallest veins, and return it to the heart, since the blood pressure is much lower on the return journey.
Their walls can be thinner.
Much thinner, yes. They have the same 3 tunicas, but the tunica media is thin with less smooth muscle and elastic tissue compared to arteries. Their tunica externa, the outer connective tissue layer, is often the thickest layer, providing support.
So they're built more for volume than pressure.
Exactly. Veins are capacitance vessels. They can hold a large volume of blood. About 65% of the body's total blood volume at any given time is in the veins. And because the pressure is low, especially in the limbs, many veins have internal valves.
Valves inside the veins, like the heart valves.
Similar principle, yes. They're formed from folds of the tunica intima and look like little flaps. They prevent gravity from pulling blood backward, particularly in the legs when you're standing. Muscle contractions around the veins help squeeze the blood upward, past these valves, milking it back towards the heart. Hashtag 2.3 major highways and special roads.
Okay, different vessel types built for different jobs. Let's zoom out a bit. What are the main highways, the major arteries leaving the heart?
The undisputed superhighway is the aorta. It arches up from the top of the left ventricle, that's the ascending aorta, then curves over like a candy cane, forming the arch of the aorta.
The big arch you see in diagrams.
That's the one. And right from that arch 3 major arterial trunks branch off to supply the entire upper body.
3 main exits, what are they?
The first one, heading towards the right, is the brachiocephalic trunk. Brachio means arm, cephalic means head. It's short and quickly splits to feed the right arm via the right subclavian artery and the right side of the head and neck via the right common carotid artery.
Okay, one trunk for the whole right side up top.
Pretty much. Then the next 2 branches arise directly from the aortic arch itself. Second is the left common carotid artery, which goes straight up to supply the left side of the head and neck.
Left head traffic. Got it.
And the third major branch is the left subclavian artery, which supplies the left arm. So 1 trunk for the right, 2 separate arteries for the left head and left arm. These are the critical intersections feeding the northern routes of our city analogy.
Clear enough. Now, you mentioned the brain's blood supply earlier. Is there anything special about how that road network is designed?
Oh, absolutely. The brain is incredibly greedy for oxygen and glucose, and it cannot tolerate interruptions in blood flow even for a few minutes. So it has a remarkable safety feature built in at its base called the Circle of Willis.
The Circle of Willis, what is that exactly? Is it one vessel?
It's not a single vessel, no. It's an actual circle or ring of interconnected arteries formed at the base of the brain. It connects the major arteries supplying the brain.
Which arteries connect there?
Primarily, it involves the 2 internal carotid arteries coming up the front of the neck and the 2 vertebral arteries coming up through the spine at the back, which join to form the basilar artery. Branches from these all link together, along with communicating arteries, to form this circle.
And what's the point of forming a circle?
Redundancy. It's a brilliant piece of natural engineering. If one of the main feeder arteries, say, one of the internal carotids, becomes severely narrowed or blocked, blood can often still reach all parts of the brain by flowing around the circle from the other arteries.
So it provides alternative routes, like the coronary anastomosis, but maybe even more critical.
Arguably more critical, given the brain's sensitivity. It's the ultimate backup system, designed to ensure continuous perfusion, even if one supply line is compromised. It significantly reduces the risk of a major stroke from a single vessel blockage.
Wow, that's incredible foresight and design. Are there any other unusual special routes in the circulatory system?
There are. The most significant examples are portal circulations.
Portal circulations, what makes them special?
Normally blood flows. Arterial, capillary bed, venule, vein, and heart.
Right, the standard path.
In a portal system, the path goes arterial, capillary bed, #1 portal vein, capillary bed, #2 venule, vein, heart.
Whoa, wait, a vein connecting 2 capillary beds. That is unusual. Why would you do that?
It allows one organ system to directly process the blood coming from another before it returns to the general circulation. The classic, most important example is the hepatic portal circulation. Hepatic means liver.
So this involves the liver.
Yes. All the nutrient-rich, but potentially toxin-laden blood absorbed from the stomach and intestines, capillary bed, #1, doesn't go straight back to the heart. Instead, it's collected into the hepatic portal vein, which transports it directly to the liver. In the liver, that blood flows through a second set of capillaries, liver sinusoids, capillary bed, #2. Here, the liver cells can process the absorbed nutrients, store glucose, detoxify harmful substances, and remove bacteria before that blood finally drains into the hepatic veins and returns to the heart.
So the liver gets the first pass at everything absorbed from the gut. It's like a processing and decontamination plant.
Exactly. It's essential for metabolism and protection. There's also another important one, the hypophyseal portal system, connecting the hypothalamus in the brain to the pituitary gland, allowing direct hormonal communication. But the hepatic portal system is the major one.
Okay, we've built the engine, mapped the roads, even the special detours, like the portal system. Now for what might be the most fascinating part, the heart's own internal electrical grid. How does it power itself and keep perfect time?
It is fascinating. It starts with the nature of the heart muscle cells themselves, the cardiomyocytes. They're specialized, they're striated, like skeletal muscle, meaning they have that striped appearance, but they're also branched.
Branched, how does that help?
The branches allow them to connect with several neighboring cells, and these connections happen at special junctions called intercalated discs.
Intercalated discs, okay. What's special about them?
These discs contain 2 important things. Desmosomes, which are like rivets holding the cells tightly together during contractions, and gap junctions.
Gap junctions. You mentioned those briefly with the fibrous skeleton. They're like tunnels.
Exactly. They are tiny electrical tunnels or channels directly connecting the cytoplasm of adjacent cells. This allows ions, and therefore electrical current, to flow directly from one cell to the next very rapidly.
Ah, so the signal doesn't have to cross a synapse like in nerves.
Correct. It flows almost instantaneously from cell to cell through these gap junctions, and this is why the heart muscle can behave as a coordinated unit.
How so?
Because of the gap junctions, when one heart muscle cell gets electrically excited, the signal spreads immediately to all its connected neighbors. This means the entire network of atrial muscle cells or the entire network of ventricular muscle cells can contract almost simultaneously, as if they were one giant cell. We call this a functional syncytium.
Functional syncytium, acting like one unit. Got it. But what starts the electrical signal in the first place? Does it come from the brain?
That's the amazing part. Mostly, no. While the brain can influence the heart rate, the heart generates its own rhythm. This is thanks to a small percentage of specialized heart muscle cells called autorhythmic fibers.
Autorhythmic, self-rhythm.
Exactly. These aren't typical contracting muscle cells. They are modified cardiomyocytes that have the unique ability to spontaneously depolarize to generate their own action potentials without needing any external nerve stimulation.
They just fire on their own.
They fire on their own rhythmically. They act as the heart's natural pacemaker system. This property is called autorhythmicity, and it proves the heart is truly autonomous. It will keep beating even if removed from the body, as long as it has oxygen and nutrients.
Wow. That's incredible. Now, you mentioned earlier something about a long refractory period being important.
Absolutely critical.
Right.
Remember, an action potential triggers a muscle contraction. The refractory period is the brief time after an action potential starts, during which the muscle cell cannot be stimulated to contract again, no matter how strong the stimulus. It needs time to reset.
Okay, a recovery period.
Yes. And in heart muscle, this refractory period is unusually long. Crucially, it lasts almost as long as the entire contraction itself.
Why is that so important?
Think about skeletal muscle, like in your arm. The refractory period is very short. This allows nerve impulses to arrive rapidly, one after another, causing the muscle twitches to fuse together into a sustained, smooth contraction, what we call tetanus. You can hold your arm flex.
Right.
If the heart muscle could do that, if it could go into tetanus because of a short refractory period, the chambers would just seize up in a prolonged state of contraction. They wouldn't relax, they wouldn't refill with blood, and the pumping action would stop instantly. It would be fatal.
Oh.
Right.
So the long refractory period guarantees that the heart must relax and refill between beats.
Precisely. It's the built-in safety mechanism that prevents tetanic contraction and ensures the rhythmic pumping cycle continues. It's absolutely essential for life. Hashtag tag 3.2, the conductive pathway, the firing order.
Okay, so the heart generates its own signal and it has a built-in safety pause. But how does that signal spread in the right order to make the chambers contract efficiently, especially given that fibrous skeleton blocking direct passage?
It follows a very specific, well-defined conductive pathway, like signals traveling down dedicated wires. This ensures the atria contract first, followed by the ventricles after that crucial delay.
So where does it start? What's the master switch?
The starting point, the heart's primary pacemaker, is the sinoatrial node, usually called the SA node.
SA node, where is it?
It's a small cluster of these autorhythmic cells located high up in the wall of the right atrium, near where the superior vena cava enters.
Okay, top of the right receiving room. And why is it the pacemaker?
Because its cells have the fastest natural rate of spontaneous depolarization. They reach the firing threshold and generate action potentials more frequently than any other part of the conduction system, typically around 70-80 times per minute at rest. They set the pace.
So they fire first and trigger everything else. What happens after the SA node fires?
The impulse spreads rapidly outwards from the SA node like ripples on a pond through the muscle tissue of both atria, thanks to those gap junctions we talked about.
Making both atria contract together.
Exactly. This atrial contraction pushes that last bit of blood down into the ventricles. As the wave spreads across the atria, it also reaches the next key component in the pathway, the atrioventricular node, or AV node.
The AV node, where's that located?
It sits low down in the septum, the wall between the right and left atria, right near the tricuspid valve and just above the fibrous skeleton.
Ah, the gateway through the firewall.
Precisely. This is the only normal electrical connection between the atrial muscle and the ventricular muscle. And something very important happens here.
The delay.
The critical delay. The impulse slows down considerably as it passes through the AV node. The fibers here are smaller in diameter and have fewer gap junctions, which naturally slows conduction speed.
And this delay is deliberate to let the atria finish emptying.
Absolutely deliberate. It typically lasts about 0.1 seconds, just long enough for atrial systole to complete and for the ventricles to receive that final atrial kick of blood before they get the signal to contract themselves. Perfect timing.
Okay, so signal delayed at the AV node. Where does it go next?
After clearing the AV node, the impulse enters the atrioventricular bundle, also known as the bundle of His. This is the bundle of conductive fibers that penetrates through the fibrous skeleton into the top part of the interventricular septum, the wall between the ventricles.
The bridge across the insulation.
The only bridge. The AV bundle then quickly splits into the right and left bundle branches, which travel down either side of the interventricular septum, heading towards the bottom tip apex of the heart.
Down the middle wall?
Yep. Finally, these bundle branches branch extensively into a network of fine fibers that spread upwards throughout the outer walls of the ventricles. Ththese final distribution fibers are called the Purkinje fibers.
Purkinje fibers. They sound fast.
They are very fast. They conduct the impulse rapidly to the contractile muscle cells throughout the ventricular myocardium. This ensures that all parts of the ventricles contract in a coordinated, powerful wave, typically starting from the apex and squeezing upwards towards the major arteries at the top.
Squeezing from the bottom up, like getting toothpaste out of a tube. Makes sense for efficient ejection.
Exactly. SA node, atrial muscle, DEEF, AV node, AD AV mode, delay AV bundle branches, Purkinje fibers, ventricular muscle. That's the precise firing order for every single heartbeat. Hashtag tag 3.3, monitoring the electricity.
ECG, EKG.
That pathway is incredibly specific, and since it's all based on electrical signals traveling through the heart muscle, can we actually measure that electricity from outside the body?
We absolutely can, and that's exactly what an electrocardiogram, an ECG, or sometimes EKG from the German spelling does.
So an ECG isn't measuring the muscle squeezing, but the electrical wave that causes the squeezing. Precisely. The ECG machine detects the tiny electrical currents generated by the heart muscle as they spread through the body tissues to the skin surface. It doesn't record a single action potential, but rather the composite sum of all the action potentials being generated by millions of heart muscle fibers during each beat.
Okay, a combined electrical picture. And this gives us those familiar wavy lines on the paper strip.
Yes. A normal ECG trace shows a series of characteristic waves, complexes, and intervals that correspond directly to the electrical events of the cardiac cycle we just discussed.
What are the main waves we see?
There are three main deflections, or waves. First, you typically see a small upward bump called the P wave.
P wave, what does that represent?
The P wave represents atrial depolarization, the electrical signal spreading from the SA node across the atria, causing them to contract shortly after the P wave begins. If the P wave looks abnormal, maybe too tall or too wide, it can suggest problems with the atria, like enlargement.
Okay, P wave, atrial activation. What's next?
Following the Q wave, after a short, flat baseline, representing the AV node delay, you get the largest, most prominent deflection, the QRS complex. It usually consists of a small downward dip, Q, a tall upward spike, R, and another downward dip, S.
QRS, that's the big spike. What's happening there?
The QRS complex represents ventricular depolarization, the rapid spread of the electrical impulse through the AV bundle branches, and Purkinje fibers, activating the large mass of ventricular muscle. Ventricular contraction begins shortly after the QRS complex starts.
So QRS equals ventricular activation. Why is it so much bigger than the P wave?
Simply because the ventricles have so much more muscle mass than the atria. More muscle-generating electrical signals creates a larger composite wave on the ECG.
Makes sense. Is there a way for the atria repolarizing, relaxing electrically?
There is, technically, but the atrial repolarization wave is usually very small and occurs at the same time as the large QRS complex, so it gets completely obscured or buried within it. You don't normally see it separately.
Okay, so P wave, QRS complex. What's the last main wave?
After the QRS complex, there's another flat segment, and then you typically see a broader, rounded, upward deflection called the T wave.
T wave. What's that?
The T wave represents ventricular repolarization, the electrical recovery or resetting of the ventricular muscle fibers as they prepare for the next beat. Ventricular relaxation, diastole, begins during the T wave.
So P is atrial firing, QRS is ventricular firing, T is ventricular resetting. That seems to cover the main electrical events.
It does, and analyzing the shapes of these waves, their durations, the intervals between them, and the segments of baseline connecting them provides a huge amount of clinical information.
Like what? Can you give an example?
Sure. For instance, the ST segment, that's the flat baseline portion between the end of the S wave of the QRS complex and the beginning of the T wave, This segment corresponds to the time when the entire ventricular myocardium is depolarized, the plateau phase of the action potential. If that ST segment is abnormally elevated, raised significantly above the baseline, it's a classic, often urgent sign of an acute myocardial infarction, a heart attack. It means some part of the ventricular muscle is injured and not repolarizing properly.
Wow. So that flat line suddenly bumping up is a major red flag.
A major red flag. Conversely, if the ST segment is depressed, pushed below the baseline, it often indicates ischemia, meaning the heart muscle isn't getting enough oxygen, perhaps due to a narrowed coronary artery, but isn't necessarily suffering irreversible damage yet.
Okay. What about other parts? Can the waves themselves give clues?
Absolutely. For example, an abnormally deep and wide Q wave might indicate a previous heart attack that has left scar tissue. A flat T wave can be seen in coronary artery disease or low potassium. An excessively tall peaked T wave might signal hyperkalemia, dangerously high potassium levels.
So doctors can tell a lot just by looking at the shapes and timings on this graph.
A phenomenal amount. They can determine the heart rate very accurately. For example, in a regular rhythm, you can count the number of large squares on the ECG paper between two consecutive R waves, the peaks of the QRS, and divide 300 by that number to get the approximate rate. They can assess the rhythm, detect arrhythmias, irregular heartbeats, identify chamber enlargement, diagnose ischemia or infarction, check for electrolyte imbalances, and even monitor the effects of certain drugs. It's an incredibly powerful, non-invasive diagnostic tool.
Okay, the electrical system dictates the timing with incredible precision, and the ECG lets us watch it happen. Now let's connect that electricity to the actual mechanics, the physical pumping cycle. How does that electrical sequence translate into blood moving through the heart? Hashtag 4.1, the cardiac cycle, diastole versus systole.
Right. The cardiac cycle encompasses all the events, both electrical and mechanical, associated with one complete heartbeat. It fundamentally involves two alternating phases for the chambers. Diastole, which is the period of relaxation and filling.
Diastole, relax.
And systole, which is the period of contraction and ejection.
Systole, contract, eject.
Okay, we can walk through the sequence, starting when the heart is generally relaxed. Let's call this late diastole.
Okay, late relaxation phase. What's happening?
During late diastole, both the atria and the ventricles are relaxed. Blood has been flowing passively from the large veins into the atria, and because the AV valves, tricuspid and mitral, are open, it's also flowing directly through the atria and into the ventricles.
So the ventricles are just filling up passively?
Mostly, yes. About 70–80% of ventricular filling actually happens passively like this, just due to the pressure gradient from the veins. The semilunar valves, aortic and pulmonary, are closed at this point because the pressure in the arteries is higher than in the relaxed ventricles.
Okay, passively filling. Then what?
Then the SA node fires, triggering the P wave on the ECG and initiating atrial systole. The atria contract.
The atrial kick.
The atrial kick, exactly. This contraction actively pushes the remaining 20–30% of blood from the atria down into the ventricles, completing ventricular filling. This marks the end of ventricular diastole. The volume of blood now in each ventricle is called the end diastolic volume, or EDV.
EDV, the maximum fill volume.
Got it. What happens next? Now the electrical signal passes through the AV node, down the bundles, and hits the ventricles, triggering the QRS complex and the start of ventricular systole.
The big squeeze begins.
Right. The ventricles start to contract, and the pressure inside them rises very rapidly. Almost immediately, this rising ventricular pressure exceeds the pressure in the atria,
Pushing the AV valves shut.
slamming them shut. And the closure of the tricuspid and mitral valves creates the first heart sound, the characteristic lub sound you hear with the stethoscope.
Lub. AV valves closing.
Now, for a very brief moment after the AV valves close but before the semilunar valves open, both sets of valves are shut. The ventricles are contracting, squeezing the blood, but the volume inside can't change because all the doors are closed.
So pressure is skyrocketing, but no blood is moving out yet.
Exactly. This is called the isovolumic contraction phase. Iso means same, volumic means volume. Same volume, rapidly rising pressure.
Okay. What makes the exit doors open?
The pressure has to keep rising until it overcomes the pressure in the arteries outside. The pressure in the pulmonary artery is normally around 10–20 millimole Hg, and the pressure in the aorta is around 80 millimole Hg. That's the diastolic pressure.
Oh.
Once the pressure inside the contracting right ventricle exceeds the pulmonary artery pressure, the pulmonary semilunar valve flies open. Once the pressure inside the contracting left ventricle exceeds the aortic pressure, the aortic semilunar valve flies open.
And now blood gets ejected.
Now we enter the ventricular ejection phase. Blood is forcefully pumped out of the ventricles into the pulmonary artery from the right and the aorta from the left. During this phase, the pressure in the left ventricle reaches its peak, normally around 120 mmHg, the systolic pressure.
Okay, blood is successfully ejected. What happens as the ventricles finish contracting?
As the ventricles finish systole, they start to relax, marking the beginning of early diastole. The T wave on the ECG corresponds to this ventricular repolarization. As the ventricular muscle relaxes, the pressure inside the ventricles starts to fall rapidly.
Pressure dropping.
And as soon as the ventricular pressure drops below the pressure in the aorta and pulmonary artery, the backflow of blood in those arteries snaps the aortic and pulmonary semilunar valves shut.
Preventing blood from leaking back into the ventricles.
Correct. And the closure of these semilunar valves creates the second heart sound, the dub sound.
Dub. Semilunar valves closing. Lub-dub. Lub-dub. Got it.
Now, for another brief period after the semilunar valves close but before the AV valves open again, all four valves are once more closed. The ventricles are relaxing, but the volume isn't changing yet. This is the isovolumetric relaxation phase.
Same volume again, but this time pressure is dropping fast.
Dropping fast. Eventually, the ventricular pressure falls below the atrial pressure, which has been slowly rising as the atria fill with blood from the veins. When this happens, the AV valves, tricuspid and mitral, drift open.
And the whole cycle starts again with passive ventricular filling.
And the whole cycle begins anew with passive ventricular filling during mid to late diastole, and it repeats roughly 75 times a minute at rest for your entire life. Tag 4.2 measuring performance, cardiac function.
That cycle is incredibly precise. Lub-dub, fill squeeze, open close. How do we measure how well this pump is actually performing its job? What are the key metrics?
There are several important ones. Perhaps the most fundamental is cardiac output, usually abbreviated as CO.
Cardiac output, what does that measure?
It's the total amount of blood ejected from each ventricle, either the left or the right. Remember, they have to be equal per minute.
The total volume pumped per minute. How is it calculated?
It's a simple multiplication. Cardiac output, CO, equals the heart rate, HR, measured in beats per minute, times the stroke volume, SV, which is the volume of blood ejected per single beat.
CO equals HRX SV. Makes sense. What's a typical cardiac output?
In a healthy resting adult, it's typically around 4 to 7 liters per minute. Think about that your heart is pumping roughly the entire volume of blood in your body, which is about 5 liters every single minute.
Wow, that's a lot of flow. And stroke volume is the amount per beat. How much is that usually?
Stroke volume at rest is typically around 70-80 milliliters per beat. Remember the end diastolic volume, EDV, the amount in the ventricle when it's full? That might be around 130 milliliters. So the ventricle doesn't eject all the blood it holds. The amount left behind after contraction is called the end systolic volume, ESV. Stroke volume is simply EDV minus ESV.
Okay, so SV equals EDV ESV. It ejects most, but not all.
Correct. And this leads to another really crucial clinical measure of heart function, the ejection fraction, or EF.
Ejection fraction. That sounds like a percentage.
It is exactly that. The ejection fraction tells you what percentage of the blood that was in the ventricle at the end of filling the EDV is actually pumped out with each beat, the stroke volume. So the formula is EF, SV, EDV by 100%.
Okay, SV divided by EDV as a percentage. Why is this important?
Because it gives a direct indication of the ventricle's pumping efficiency, particularly the left ventricle. A normal ejection fraction is typically around 55% to 70%. It means the ventricle is effectively ejecting well over half the blood it contains with each beat.
And if it's lower than that?
An EF significantly below, say, 50% or especially below 40% often indicates impaired ventricular function. The pump is weakened, perhaps due to damage from a heart attack, long-term high blood pressure, or valve disease. It's a key indicator used to diagnose and monitor heart failure. It tells you immediately if the engine isn't running on all cylinders, so to speak. Hashtag TAG 4.3, regulating the engine. Control of BP and CO.
Okay, we can measure performance with CO and EF. Now, how does the body control this system? How does it regulate the pressure and the output? Let's start with blood pressure.
Right, blood pressure BP is simply the force, the lateral pressure, exerted by the circulating blood against the walls of the arteries. We measure it in millimeters of mercury.
And we usually get two numbers, right? Systolic and diastolic.
Correct. Systolic pressure is the peak pressure reached in the arteries during ventricular ejection. Systole, normally around 120 mmHg. Diastolic pressure is the lowest pressure in the arteries, occurring during ventricular relaxation, diastole, when the aortic valve is closed normally around 80 mmHg. So we'd say 120 over 80.
Got it. What determines that pressure level?
Fundamentally, blood pressure is determined by three main factors, and they're interconnected. First, cardiac output, CO. The faster the heart beats, or the more blood it pumps per beat, stroke volume, the higher the pressure tends to be.
More flow equals more pressure.
Makes sense. Second, total blood volume. The more fluid there is within the closed system of blood vessels, the higher the pressure will be. Think of overinflating a tire.
More volume, more pressure. Okay.
And third, peripheral resistance. This is the friction or opposition to blood flow, primarily in the arterioles. The narrower the vessels, vasoconstriction, the higher the resistance, and the higher the blood pressure needed to push blood through them.
Narrower pipes mean higher pressure.
Right.
So BP depends on CO, volume, and resistance.
Exactly. And the body constantly monitors and adjusts these three variables to keep blood pressure within a safe and effective range.
Let's focus on cardiac output for a moment. We know CO equals HRX SV. How does the body control stroke volume, the amount pumped per beat?
Stroke volume itself is determined by three main factors. Think of them as how much the heart fills, how hard it squeezes, and how much resistance it pushes against.
Fill, squeeze, resistance. Okay, let's break those down. First, filling.
The filling relates to preload. Preload is technically defined as the amount of stretch on the ventricular muscle fibers just before they contract. Essentially, it's directly related to how much blood has filled the ventricle in the end diastolic volume, EDV.
So more filling means more stretch, means higher preload.
Correct. And the relationship between preload and contraction strength is described by a very important principle, the Frank-Starling law of the heart.
Frank-Starling law, what does it state?
In simple terms, it states that within physiological limits, the more the ventricular muscle fibers are stretched during filling, i.e. the higher the preload or EDV, the more forceful the subsequent contraction will be, and thus the greater the stroke volume.
So the heart automatically pumps out more blood if more blood comes back to it.
Exactly. Think of it like stretching a rubber band. The further you stretch it back, more preload, the harder and faster it snaps forward when you let go. Stronger contraction, higher stroke volume. It's an intrinsic property of the heart muscle itself.
That's a beautiful self-regulation mechanism. What affects preload then?
Primarily two things. The rate of venous return, how much blood is flowing back to the heart from the veins, and the duration of ventricular diastole. How long the ventricle has to fill a slower heart rate allows more filling time.
Okay, preload Frank-Starling is the first factor for SV. What was the second? Squeeze.
Right, the inherent squeeziness or strength of the muscle contraction independent of the stretch. This is called contractility, or sometimes inotropy.
Contractility. Is this something the body can change?
Oh yes, contractility is significantly influenced by external factors, particularly hormones and nerve signals. Substances that increase contractility are called positive inotropic agents.
Like what?
The classic examples are hormones like epinephrine and norepinephrine, adrenaline and noradrenaline, released during stress or exercise. Increased calcium levels in the cell also boost contractility, as does thyroid hormone. These things basically make the heart muscle squeeze harder for any given preload. They're like stepping on the accelerator for the heart muscle itself.
Okay, positive inotropes increase the force. Are there negative ones?
Yes, negative inotropic agents decrease contractility. Examples include acetylcholine, released by the parasympathetic nervous system to slow the heart, high levels of extracellular potassium ions, and conditions like acidosis, increased acidity of the blood. These factors weaken the force of contraction.
So preload is about filling, contractility is about the inherent strength of the squeeze. What was the third factor for stroke volume? Resistance.
Yes, the resistance the heart has to pump against. This is called afterload.
Afterload. Can you explain that a bit more?
Afterload is specifically the pressure that the contracting ventricles must overcome before the semilunar valves, aortic and pulmonary, can even open and ejection can begin. Think of it as the pressure load the heart works against after it starts contracting.
So for the left ventricle, the afterload is essentially the pressure in the aorta.
Primarily, yes.
Okay.
It's closely related to aortic pressure and the resistance in the systemic circulation. If someone has high blood pressure, hypertension, the pressure in their aorta is chronically elevated. This means their left ventricle has to generate much higher pressure during that isovolumic contraction phase just to force the aortic valve open. This increased afterload makes it harder for the ventricle to eject blood.
Like trying to push open a very heavy, sticky door.
Exactly. Increased afterload from things like hypertension or stiff, narrowed arteries due to atherosclerosis opposes the ejection of blood. So if afterload goes up, stroke volume tends to go down, assuming preload and contractility stay the same. And importantly, chronically high afterload puts a huge strain on the heart muscle over time, potentially leading to heart failure. Hashtag 4.4, the short-term and long-term controls.
Okay, so stroke volume depends on preload, contractility, and afterload. And the body regulates blood pressure by influencing cardiac output, volume, and resistance. How does this regulation happen? Are there fast and slow systems?
Yes, there are both short-term rapid adjustments, primarily handled by the nervous system, and long-term slower adjustments, mainly involving hormones and the kidneys controlling blood volume.
Let's start with the short-term fixes, the nervous system reflexes.
Right. These rapid adjustments are coordinated mainly by cardiovascular centers in the medulla oblongata, part of the brainstem. The key player here is the vasomotor center, which controls the diameter of blood vessels, especially arterioles.
The vasomotor center in the medulla. How does it know what to do?
It constantly receives input from various sensors throughout the body. The most important are baroreceptors.
Baroreceptors, pressure sensors.
Exactly. These are specialized nerve endings located in the walls of the aortic arch and the carotid sinuses, at the branching of the carotid arteries in the neck. They are stretch receptors, sensitive to the degree of stretch in the arterial walls.
So they measure how stretched the arteries are, which corresponds to pressure.
Precisely. Let's say you stand up quickly. Gravity causes some blood to pool temporarily in your legs, venous return drops slightly, cardiac output falls, and therefore your blood pressure momentarily dips.
Right, sometimes you feel a bit dizzy.
That dizziness is the brief drop in pressure. But immediately, the baroreceptors in your aorta and carotid arteries sense less stretch. They respond by sending fewer inhibitory nerve signals up to the vasomotor center in the medulla.
Fewer inhibitory signals, so the center becomes more active.
Exactly. Less inhibition means the cardiovascular center increases its sympathetic nervous system output to the heart and blood vessels.
Sympathetic, fight or flight.
That system, yes. Increased sympathetic stimulation does three things almost instantly. 1, increases heart rate. 2, increases contractility, stroke volume. 3, causes widespread vasoconstriction, narrowing of arterioles, which sharply increases peripheral resistance.
Faster rate, stronger beat, tighter vessels.
All three actions work together to rapidly increase cardiac output and peripheral resistance, which brings your blood pressure right back up to normal, usually within seconds. That's why the dizziness is usually very brief. The baroreceptor reflex is incredibly fast and effective at buffering short-term pressure changes.
Amazing. Are there other sensors involved in short-term control?
Yes, there are also chemoreceptors located near the baroreceptors and also in the brainstem. These monitor the chemical composition of the blood, primarily levels of oxygen, O2, carbon dioxide, CO2, and hydrogen ions, acidity, pH.
What do they trigger?
If, for example, oxygen levels fall too low, or CO2 or acidity rise too high, indicating respiratory distress or poor tissue perfusion, these chemoreceptors send stimulatory signals to the cardiovascular centers. This usually results in increased sympathetic output to raise blood pressure and improve blood flow, often alongside signals to increase breathing rate.
Okay, so baroreceptors for pressure, chemoreceptors for blood chemistry, both feeding into the medulla for rapid adjustments via the sympathetic nervous system. What about the long-term controls? You mentioned hormones and kidneys.
Right. Long-term regulation focuses primarily on controlling total blood volume, which is a major determinant of blood pressure over hours, days, and weeks. The kidneys are the star players here.
How do the kidneys control blood volume? By adjusting urine output.
Precisely. They can conserve water when blood volume or pressure is low and excrete excess water when volume or pressure is high. This is largely orchestrated by hormones.
Which hormones are key?
One of the most powerful systems is the renin-angiotensin-aldosterone system, often called the RAA system.
RAA system. Okay, how does that work?
It gets triggered when blood flow to the kidneys decreases or when blood pressure drops. Specialized cells in the kidneys detect this and release an enzyme called renin into the bloodstream.
Okay, renin released when pressure is low.
Renin then initiates a cascade of reactions. It converts a plasma protein called angiotensinogen, made by the liver, into angiotensin I. Then another enzyme called ACE, angiotensin-converting enzyme, found mainly in the lungs, converts angiotensin I into the active form, angiotensin II.
Angiotensin II, is that the important one?
That's the powerhouse molecule. Angiotensin II has multiple effects, all aimed at raising blood pressure. First, it's an extremely potent vasoconstrictor. It directly causes arterioles throughout the body to clamp down, significantly increasing peripheral resistance and thus BP almost immediately.
Okay, direct vasoconstriction. What else?
Second, angiotensin II travels to the adrenal glands, which sit on top of the kidneys, and stimulates them to release another hormone called aldosterone.
Aldosterone. What does it do?
Aldosterone acts on the kidneys, telling them to reabsorb more sodium ions, salt, from the filtrate that would normally become urine, and wherever salt goes, water follows by osmosis. So aldosterone causes the kidneys to retain both salt and water.
So it reduces water loss in urine.
Exactly. By conserving salt and water, aldosterone helps to increase the total blood volume over time, which contributes to raising blood pressure back towards normal. So the RAA system raises DP both quickly via angiotensin II's vasoconstriction and more slowly via aldosterone's effect on blood volume.
That's a powerful system for raising pressure. Are there other hormones involved in volume control?
Yes. Another important one is antidiuretic hormone, ADH, which is also known as vasopressin.
ADH. Antidiuresis means less peeing.
Correct. ADH is released from the pituitary gland in the brain, primarily in response to dehydration, increased blood concentration, or a significant drop in blood volume or pressure.
And what does ADH do?
It acts directly on the collecting ducts in the kidneys, making them more permeable to water. This allows more water to be reabsorbed from the filtrate back into the bloodstream, thus conserving body water and increasing blood volume.
So ADH also helps raise volume and pressure. Does it do anything else?
Yes. At high concentrations, ADH also causes vasoconstriction, hence its other name, vasopressin. So it contributes to raising pressure in two ways as well.
Okay. RAA and ADH both work to increase blood volume and pressure. Is there anything that works the other way to lower pressure if it gets too high?
Absolutely. The body needs a counterbalance. That role is played primarily by atrial natriuretic peptide, or amatrial.
Meaning from the atria of the heart, natriuretic, promoting salt excretion.
Exactly right, on both counts. ANP is a hormone released by muscle cells in the walls of the atria when they are stretched excessively, which happens when blood volume and pressure are too high.
So the heart itself senses when it's being overloaded.
Yes. It's another amazing feedback loop. When the atria release ANP, it has effects that are essentially the opposite of the RAA system in ADH.
How so?
ANP promotes vasodilation, relaxing arterioles, and thus decreasing peripheral resistance. It also acts on the kidneys to increase the excretion of sodium and water in the urine, natriuresis and diuresis. This reduces total blood volume.
So it lowers resistance and lowers volume.
Correct. Both actions work together to bring elevated blood pressure back down towards the normal range. ANP is the body's natural way to counteract volume overload and hypertension. It's the essential off switch or relief valve in the system. #outro.
Wow. That brings us, I think, to the end of this incredibly detailed deep dive into our internal transport network. We really covered a lot of ground.
We certainly did.
We started right inside the chest, locating the heart in the mediastinum, appreciating why that left ventricle is so thick. We mapped the plumbing, the chambers, the crucial one-way valves held by those tiny parachute strings, and the vital electrical insulation of the fibrous skeleton.
Then we hit the road network, the arteries built for pressure, the arterioles as traffic controllers, the absolutely essential exchange happening at the microscopic capillaries, and the veins bringing it all back, not forgetting the heart feeding itself via the coronary circulation and those amazing backup routes, the anastomoses or the brain circle of Willis.
And the electrical grid, the heart's ability to pace itself with the SA node, that critical AV node delay, the precise pathway ensuring coordinated contraction, and the long refractory period preventing seizure. Plus, how the ECG lets us eavesdrop on that whole electrical conversation.
Right. And finally, we tied it all together with the mechanics of the cardiac cycle, lub-dub, systole, diastole, and the complex, multi-layered control systems, from the immediate reflexes of the parareceptors, adjusting beat by beat,
to the slower but powerful long-term hormonal management of blood volume by the kidneys, orchestrated by the RAA system, ADH, and balanced by ANP from the heart itself. It really drives home that the heart isn't just a muscle.
Not at all. It's this completely autonomous, self-regulating, electrical, hydraulic, and even endocrine machine. It senses, responds, and maintains balance in ways that are just awe-inspiring.
Absolutely.
And it relies on that perfect equilibrium. We talked about how the left ventricle is so much stronger than the right, pumping against maybe 5 or 6 times the resistance to push blood all around the body, while the right just pushes it next door to the lungs.
Right, a huge difference in workload.
Yet, and here's something perhaps to leave you thinking about, despite that massive difference in strength and the pressure they generate, the volume of blood ejected per beat, the stroke volume from the powerful left ventricle must be exactly identical to the stroke volume from the much weaker right ventricle, beat after beat after beat.
Identical. Even though the left is working so much harder, why is that absolute balance so critical?
Well, think about it. If the left ventricle consistently pumped out even just slightly more blood into the systemic circulation than the right ventricle pumped into the pulmonary circulation, where would that excess blood coming back from the body end up?
It would overwhelm the right side and back up into the lung.
Exactly. Blood would rapidly accumulate in the pulmonary circulation. Conversely, if the right pumped more than the left, blood would back up in the systemic veins. Very quickly, this imbalance would lead to severe congestion, either pulmonary edema, fluid in the lungs, or systemic edema.
So they have to stay perfectly matched, liter for liter, minute after minute.
They absolutely have to. That mandatory equality of stroke volume, despite facing vastly different afterloads driven by mechanisms like the Frank-Starling law, ensuring output matches input for both sides simultaneously. Well, that truly highlights the heart's self-regulation as the ultimate marvel of biological engineering.
A perfectly balanced, life-sustaining marvel. That's a great place to leave it. Thanks for joining us on The Deep Dive.